Hello again. In our last lectures, we've learned about the FFT and what a powerful method that is for computing the steady-state response of both single and multi-degree of freedom systems. It's a simple process where we take, using the FFT for example, we can take the forcing over one period, we're assuming it to be periodic, and we convert that into some complex amplitudes of all of the different harmonics that approximate that forcing. And so the FFT gives us both the amplitudes and tells us what the frequencies of those that correspond with those amplitudes. And then each one of these is a steady state vibration problem. So we can use algebra just as we've done for simple steady-state vibration problems to solve for the complex amplitudes of the response. And then if we want the time function back, we can use the IFFT to do that. So this is an amazing tool, and it's one that I use a lot. It's really useful. But what can go wrong? What do we need to worry about here? First, we'll talk about one thing that can go wrong, which is leakage. So again, let's suppose that we have some forcing. Let's say it looks like that, and it ends right here at period t. We define a time vector and we sample that. And when we do the FFT, as you see above, we'll end up with a bunch of frequencies that this will be defined at. We'll get the complex amplitudes at 0 radians per second, omega 1 radians per second, 2 omega 1, ... up to n over 2 omega 1. And recall that omega 1 is the lowest frequency that can fit within this period, or it's 2 pi over capital T. All right, so notice that this only has a finite number of frequencies in it. And the spacing between these two and between all of them doesn't depend on, it's independent of n, it only depends on t, on how long our observation window is, how long our signal is. So one place we can run into trouble, especially with regard to sampled data, if you were doing this analytically, this doesn't tend to be a problem. But if we're given some sampled data, for example, we can run into trouble because it's possible that our signal has a frequency of, say, 1.5 omega 1. Right? What would happen in that case? So that's halfway between two of the frequencies that we have here. So just working that out in a little more detail. So the period of that signal would be 2 pi over its frequency, 1.5 omega 1. And 2 pi over omega 1 is just t. So we can rewrite this as 2 pi over omega 1 times 2/3. Or this is t, so this is just 2/3 t. Right? Or in other words, what this is telling us is if we have a period t, that we're talking about a signal that goes through one cycle in 2/3 of a period. So in the second third of a period, it'll go through only half a cycle. Now this looks okay at first, but then remember, we're assuming this is periodic, so the FFT is going to replicate this afterwards. And if we replicate it again, right? Now this signal is very different from, just a cosine of 1.5 omega 1t, right? This is not at all like a cosine function. So the Fourier series expansion of this will be very different. So again, this is called leakage, and it's describing a phenomenon where the frequency content doesn't exist right at the spectral lines in the FFT. If we were to plot, say, the G sub n versus frequency, these only exist at certain frequencies that are spaced by omega 1. Guess I should move this over to be precise. And so leakage occurs when we have a frequency that's between these. And so its energy will leak out onto other frequencies. So we can see this in a MATLAB example here. So all this code is doing is it's setting up the sampling parameters, creating a time vector, creating a sinusoidal signal that's sampled, and then taking the FFT and plotting that. So a really simple code, but watch it what we're going to do. So notice that our period is t. So, our period t is equal to pi. So omega 1 will be 2 pi over pi, or it would be 2 radians per second. So the frequencies that we're going to have are going to be 0, 2, 4, ... up to n over 2. So if we take a frequency of 16, that lands right on one of our spectral lines, right? So this will show you what happens when everything works as it should. So here's our time signal. Here is the FFT, and it correctly tells us that we have a signal that has a frequency of 16 with an amplitude of 1, and all of the other frequencies are 0. And over here you can see the actual sampled signals, or the sampled signals. We have maybe 8 or so samples, or 8 or 10 samples per period. All right, well, what happens if we take 17? Because, here in this frequency vector we'll have 16 and then we'll have 18. 17 is exactly between the frequencies that we have. So, if we do that, oops. If we take 17 instead and rerun this, now watch what happens. Things look pretty similar, though if you think about it, this is exactly the case I just talked about. The next sample here would be the first sample, so we get kind of a double peak there. And look at what happens to the FFT. Rather than giving us the correct frequency with an amplitude of 1, it tells us that, well, there's a little bit of amplitude at 16, a little bit at 18, a little bit at 14, a little bit at 20, and so on. So the energy for this sinusoid is leaked out onto other frequencies. All right? So that's leakage. And, you could play around with this. If we get a little closer to one side, you can see that the amplitude error is less bad, but there still is some amount of leakage. And another thing we could do, let's suppose we take one. Okay, well, there's lots of other cases we could look at, but we could also say we looked at a frequency of 3, right? This is one of the lower frequencies in our spectrum. So here, the difference seems less severe. We're able to, the leakage is a little less bad than it is. In contrast, if we took 65, then things look really bad. And it's interesting to note that in this case, even the time signal looks like something's funny is going on. We're sampling the signal in such a way that there seems to be like a low frequency beat to it. And that isn't real. I mean, the signal is still a sinusoid, but the points that we're seeing when we connect them with our eye, that's not quite right. So this is a frequency that's halfway between 0 and our maximum frequency. Okay, so that's leakage. The other thing that we want to talk about is aliasing. And aliasing occurs when the frequency in the signal is greater than the maximum frequency, or when omega is greater than n over 2 times omega 1. We could also, another way to define this, omega max, we can also talk about the sample frequency, which is 2 pi over delta t. And we can go through a derivation to show that, that omega max is equal to 1/2 omega sample. Right. So aliasing occurs when our frequency is too fast for our sampling. Let's look at a case study on this as well. So here, we've set n as 2 to the 7th. And for those of you who don't have your powers of 2 memorized, that's 128, right? So if omega 1 is 2, so 2 times 128 divided by 2. So n over 2 would be 128 over 2, but our omega 1 is 2 radians per second. So anyway, our highest frequency is 128. Okay, so let's just look at what happens if we have a signal of 128. Interestingly, every single time we've basically sampled on 0. Because it's a sinusoid, we get 0. Things completely go haywire. Okay, so let's see what happens if we go just a little higher than that. So we go 130. What it looks like we have is a beat frequency, right? Our signal looks like it's beating in the time domain, but the important thing to note here is that the true frequency is 130, and the FFT thinks that that frequency is 126. So when we get aliasing, the frequency basically reflects off of this line and starts to move backwards. So the frequency that we think we have is different from the true frequency. And if we move even farther beyond the sampling frequency, we reflect back even farther, and we see this move farther and farther. Now it's important to recognize that there's nothing wrong with our time data. This time data still are samples that are valid for a signal that has that frequency. And we could show that if I just add a line to that figure. Let's say we add one to this figure. And if we create a time vector that's sampled much more quickly, actually t over n. Actually, let's just do it this way. Let's take t over. We'll just go 10 times faster. So we'll add a line where we do this, and then we do sine of omega n times that time vector. And we'll make it black so we can tell it apart. Okay, so if we look here, you see that if we had the ability to see all the points in between the ones that we'd sampled, we'd still have the sine wave hiding there. And there's no error in any of these samples, right? Every one of them lands exactly on the true time function, but we just don't sample fast enough to see it, to recreate it correctly. Okay, so anyway, so that's aliasing. That's what happens to our signals if we don't sample quickly enough. And it's not a fault of the FFT, it just has to do with the sampling that we've done. Okay, so those are our two main phenomena, sampling and aliasing. By the way, an interesting little tidbit, when you talk about music, well, and the standards for this are kind of changing nowadays with compressed audio. So you have to go back to a compact disc to actually see uncompressed digital audio. But in a compact disc, the sample rate would be right around 44 kilohertz. There was actually a fraction to that, I think. So there's 44,000 samples per second. So the maximum frequency that you can carry in an audio file is 22,000 hertz. So any frequency above that won't be recorded or will be mirrored down to lower frequencies. This is convenient though because our ears can't hear beyond about 20,000 hertz. Dogs and things can hear higher, but humans' hearing tends to end at about somewhere between 15,000 and 20,000. 20,000 hertz tends to be higher for younger people. I've played sounds generated out of MATLAB in class, and we gradually step up the frequency, and you definitely do see that some people will stop hearing at around 15,000 hertz, and there are usually some people in the class that still claim to be able to hear it up to about 20,000. So anyway, okay, so that's aliasing and leakage. As long as we watch out for both of those things, we shouldn't have any problem solving vibration problems, solving steady-state vibration problems with the FFT. The last thing I want to talk about today is the fact that we can use FFT to solve some transient vibration problems. And if you're paying attention, you'll say, wait, that shouldn't be possible. FFT, the first thing that it assumes is that both the forcing and the response are periodic, right? How could we do this? Well, we can do this by just a relatively simple trick. Let's suppose that the force that we want to find the response to is this pulse right here. We'll see that this is very relevant to what we'll do later in class. So anyway, this is our pulse, and the pulse lasts 0.1 second, or say 1 millisecond. So we hit something with say a rubber or wooden hammer or something like that. All right, so if we tried to use FFT on this, and we set t right here, then we'll get big errors in the response, because the FFT would be assuming that this pulse repeats itself, right, every t seconds. And so it would actually solve a steady-state vibration problem where we're getting hammered with that pulse repeatedly, not the one where we have a pulse and then everything goes quiet. So, so that won't work. But if we use what we know about vibrations and think about this a little, what do we expect the answer to be if we applied only the pulse in blue? Right? Well, any system, single, multi-degree of freedom, there could be many frequencies in there, but all of those frequencies all of those modes will be governed by an e to the negative zeta r omega r times t, or all of them are going to decay with time. So if we sample long enough, eventually the signal will go to 0. So this is what we can do. We can trick the FFT by choosing our period to be out here. So we just include enough zeros after the force is done that the response would die to 0. If we're successful, then what we're simulating is this transient response followed by the same thing repeating itself again. Right? But that doesn't matter. As long as we get the answer, as long as we have all the information we need by the time we reach t, we don't care if the signal repeats itself again. So basically the only trick to using FFT for transient response is to choose t large enough. And how do we do that? We can actually work this out. So for a 1 degree of freedom system, we can work it out, and you could do this on a multi-degree of freedom system just by applying this to every mode. So if we have 2e to the negative zeta omega nt is our decay, how large does t need to be so that we'll get an accurate result? We'll define what's called a time constant to help with this. So this is 1 over zeta omega n. And that just lets us rewrite the exponential as e to the minus t over tau. So every time t equals tau, we've gone through one time constant. So when t equals tau, we get e to the minus 1. So that's just 1 over 2.7, right? And if you've had controls, you've maybe learned that e to the minus 4.6 would be 0.01. So that's starting to sound pretty negligible, right? If we start here with a value of 1, by the time we reach here, we'll have a value of 0.01. Okay. So, oh, sorry. Yeah. Okay, so what we would typically do, and this is kind of neat actually, if we choose that t be greater than 8 tau, let's see what happens there. So that's about twice the 1% factor. So if we plug in here, t is 2 pi over omega 1, the smallest frequency, and we're saying that that's going to be greater than or equal to 8 over zeta omega n. Now, what does this look like in the frequency domain? That's the reason we're doing this. We're wondering how would this look if we were to look at the forcing, say, versus frequency. Remember, everything is spaced by omega 1. So we can rearrange things a little, and we can write that omega 1 is pi over 8 times 2 zeta omega n. And I've rearranged it that way on purpose because this is something called the half-power bandwidth. So if we have a 1 degree of freedom system and we have a resonance, the half-power bandwidth is defined as the point where we come down by 0.707, so the square root of 2, but power is the square of velocity, so that's the half of the power in the signal. So if we come down by half the power, then the width here is 2 zeta omega n. And that's derived in the book if you want to see the full thing. So what this is saying is that omega 1, which is the frequency spacing, is roughly 0.4 times 2 zeta omega n, or 0.4 times the half-power bandwidth. Or in other words, if our first sample, say, happens right here, partway into the peak, we're guaranteed that we'll get at least one other sample in the half-power bandwidth. So we'll have more than 2 samples per half-power bandwidth. So this is just something really beautiful about the mathematics of the Fourier series, that if we think about an FFT in the time domain and wanting to capture the response until it decays to 0, in the frequency domain, that's exactly equivalent to saying that when I define this frequency response function in the frequency domain, that I want to have enough points to be able to resolve the peak. And those two criteria go hand in hand. So if I don't sample long enough, I won't get enough resolution. If I sample plenty long, then I'll get a really good resolution, and I'll be able to easily resolve how high the peak is. And this height of the peak tells us about the amplification, right? How much a signal is amplified at resonance. So if you get one right, you get them both right. So that's just a beautiful thing in the theory here. I guess on the corollary, though, the pessimistic view is this is also an example of no free lunch, right? You, in the time domain, you have to sample for a long time to see signals decay away. If you go to the frequency domain, you don't escape that, right? There's no way around that problem. And so we'll wrap up just by talking about the fact then that using Fourier series now, we can solve both steady state problems, we can solve transient problems. And so this idea of a Fourier transform just becomes fundamental to how we think about vibration problems. Given a force, we convert that to a force in the frequency domain. Usually I use capital F for that. We multiply that times some transfer function, and out comes a response in the frequency domain. And if we want to, we can go back to the time domain. So any phenomenon we can really think about this way. So if we have some force, in the time domain, it's really tricky to think about what that might do to a system. But in the frequency domain, the only thing that matters is, what frequencies are excited. Say we had a signal like this, and then it decays to 0, right? This would be, say, the magnitude of f. We're going to multiply that by a transfer function. And so basically this tells us, which modes might be excited, right? And if we have a system, say, that has 3 resonances, well, let's say even more than that, right? We can see already that the response is going to have strong components here, and probably not very much at these frequencies. All right, so looking at the spectrum, we can kind of imagine what's going to happen and what kind of response we're going to have. And so we know in the time domain, then our signal might look like, a low frequency at a high amplitude with something even higher superimposed on top of it. Right? So once you understand this, you can kind of think of anything and start to imagine what's going to happen. Same thing with transients or impacts. Say we apply this impact to a system that's really slow, really broad, right? When we take the Fourier series expansion of that, we'll see something like this, that's really falling off quickly with frequency. In contrast, if we have a sharp impact, maybe a metal hammer, if this is a rubber hammer, this would be, say, a metal hammer. Or, if you're working for the military, that could be a bullet hitting your structure rather than, crashing into a bush, crashing into a tree versus crashing into a metal barrier, right? But that will have a much broader frequency spectrum. Eventually it will have to die off, and I don't know exactly how it would. But so that has the potential to excite a lot more resonances and to get more modes that have to be considered to think about what's going to happen. So we use this for all kinds of things. We're going to use this to understand sensors and to understand what sensors are capable of measuring and what they aren't. All sensors, it turns out, have transfer functions. So, if the h of omega for a sensor, some of the sensors we're going to see have transfer functions that look like this. Actually, let me exaggerate that a little more. That look like this. So at these frequencies, the signal is going to be lost. At these frequencies, the signal would be distorted, right? And in this range, we can get an accurate measurement. We'll talk about that later when we talk about accelerometers. Okay, so I'll encourage you to start thinking about things this way. If I have time, I'll post another example where you can kind of really see this with sound reproduction. But that concludes our lecture for today. We will see you next time.